Yeah, all right. Thank you. So I'm Colin. I'm going to start and give first a bit of an overview about what bicep data looks like, and then Dominic is going to take over and give a little bit more of a detailed discussion on a kind of specialized topic that we'll get to. So what we have here is the BICEP Keck overview. This photograph is literally an overview of the Keck array looking down into it. And so these are a series of experiments that operate at the South Pole. As you can see, and these are small aperture telescopes. You can see our winner over Robert here for scale and the size of the 5 apertures in the Keck array instrument. So as I mentioned, it's a whole series of experiments. If you can go back to BICEP 2 that started observing in 2010. And so this is more than 10 years now of continuous data from very similar instruments evolving over time and all observing from 2 platforms down at the South Pole. So we had BICEP 2 that observed only at 150 gigahertz with a single focal plane, a single 26 centimeter aperture telescope. It was then we phased in the Keck array on top of that, and so the Keck array was essentially 5 BICEP 2s. So again, these 26 centimeter apertures, focal planes that looked like essentially the same construction. But the nice thing about Keck array is because you have these 5 modular telescopes, we were able to alter the frequency composition of the instrument over time. And so ultimately that Keck array data set includes data at 95, 150, 220, and 270 gigahertz. And what time periods that data is from varies. So initially Keck array was deployed all at 150 gigahertz, and then we phased in some 95 and some 220, and then the 270 was kind of a recent and still experimental addition. So in the meantime, BICEP 3 was added, and this is now a larger aperture, a 50 centimeter aperture, still of course quite small compared to something like ACT or SPT, and so low resolution in terms of angular resolution, but still large, about a factor of 2 larger in aperture diameter from BICEP 2 or Keck array, yields a much larger focal plane, which we can see a photograph of here. And it's a single telescope observing just at 95 gigahertz, but with an equivalent number of detectors in that large single focal plane to the entire 5 telescopes of Keck array. So it's scaled up significantly. Then starting last year, we've begun deploying BICEP array. So there's a photograph of BICEP array here. It will eventually consist of 4 BICEP 3 scale telescopes. So as you can see in the photograph, there's one large telescope, which is the BICEP array telescope, the first BICEP array telescope. And then we stuck 3 of the Keck telescopes into the mount because we had empty spaces because the remaining 3 telescopes are still being built. So the way it's currently operating right now has one BICEP array size telescope that's a mix of 30 and 40 gigahertz detectors. And then it has 3 of the high frequency Keck array telescopes. So 2 of these are observing at 220 gigahertz and one's observing at 270 gigahertz. So that's its current status. What we're going to do eventually is shown in this set of 4 focal plane images down below, is that eventually it'll have this 30, 40 gigahertz telescope, which is the one that exists right now. That's this light red color in the back. A 95 gigahertz telescope, which will be similar in detector count and sensitivity to BICEP 3, 150 gigahertz telescope, and then a high frequency telescope that will be a mix of 220 and 270 gigahertz detectors. So that's these sort of, both the history and the future plan. So all of these instruments are, so we're searching for B-mode polarization to constrain inflation. And the strategy that's being used for BICEP and has been used over a long time is to go very deep on a small region of sky. So I have an image of a Planck dust map here, but I've just highlighted this region here, which is the BICEP2 Keck observing field. And what's actually shown here, these highlighted pixels are, all of the pixels that are hit in the in our maps that have non-zero hits in our maps. But because of the large field of view of these telescopes and the scan strategy, these maps, the sensitivity of these maps are highly concentrated towards the middle. So really, when you think about the kind of effective F-sky, if you do some sort of inverse noise weighting on these maps, it's only about 1.5% for the BICEP2 or Keck array maps. And then for BICEP3 and BICEP array, this region does grow somewhat, not so much because we increase the scan size, but simply because the instantaneous field of view of those instruments are larger by about a factor of 2. And so this region will kind of grow all around, though actually we didn't, for BICEP3 and BICEP array, we, knowing that it was growing, we also shifted it slightly away from the dust. So the effect is that it grows more on one side than on the other. So again, thinking about, sort of how these data sets would complement others, obviously so we're not providing information at high L, at small angular resolution, because these are small aperture telescopes. We're not providing it over very much of the sky. We're going very deep on a small region. But again, what BICEP has done is gone very, very deep. And so this is from BK15, that this was our analysis of all the data through 2015. It includes only BICEP2 and Keck array. It doesn't include any BICEP3 data yet. This is showing the map depth in terms of the NL for a BB spectrum, and also an effective F-sky that's also derived from the BB spectrum. And so you can see this effective F-sky at the 3 frequencies is about 1.5%. It falls off a little bit at low L because of our filtering, which I'm going to talk about. But then you can see that these, so that the NLs are really quite low. And if you want this in terms of like a micro K arc minute map depth, this 150 gigahertz curve in green here corresponds to a map depth of like 2.9 micro K arc minutes. So this is very, very deep. And actually in an upcoming publication, which is getting really, really close, where we extend the data set up through 2018 and fold in BICEP3, then all that BICEP3 data at 95 gigahertz is going to cause this 95 gigahertz curve to drop down to around where the 150 gigahertz is. So we're talking about it at 2 different frequencies on this patch of sky, having map depths that are slightly below 3 micro K arc minutes. So very, very deep. And the 220 gigahertz map depth will also come down by a large factor too, because that new analysis is including a lot of Keck array data at high frequencies. Okay, so I'm going to talk now a little bit about what our data actually look like. So here's some example time streams. So this is one block of our, our standard observing schedule, what we would call a scan set. Takes about 50 minutes. And during that time, our telescope motion is just a, roughly 60-degree scan in azimuth, because we're at the South Pole, that azimuth direction exactly maps onto right ascension. So this is some kind of marginal weather, right? It's weather that's still passing cuts and being included in our maps, but it's not great weather. So what you can see is when we take the sum of 2 orthogonally polarized detectors in a pixel, which is measuring the temperature signal, that's quite sensitive to the atmosphere. And we can see this as we're scanning back and forth, we can see these scan synchronous signals that are showing lumpy atmospheric structure. However, when we take the difference of those 2 detectors to measure polarization, that really cleans up, and that's this bottom plot. And so that's showing that the atmosphere is mostly an unpolarized signal. And what we're seeing here is it's not purely white noise, right? Obviously, you can, even see by eye some kind of non-white variations over the course of the scan, but it's it's white down to well below hertz frequencies, and is white for large significant fraction of our science band. Okay, so in our standard pipeline, how we then build maps is, so we do not attempt to construct any sort of unbiased map. We're doing some heavy filtering on our data and binning this into maps. So in particular, the filtering, if we go back and look at this scan set here, we are on each of these back and forth azimuth motions. For each detector, we fit and remove a third order polynomial in azimuth. So that's at each half scan, which is roughly a kind of 30-second time scale. Then over that entire scan set, about 50 minutes, we're going to average that down in azimuth to find for each detector what's the azimuth fixed signal, something that's fixed in azimuth and therefore is not rotating with the sky over 50 minutes. We're going to subtract that off. And then at the CMB phase, which is a 9-hour time scale in our observing schedule, we will deproject a monopole and dipole temperature depolarization leakage for each detector pair. And so the monopole term would be if you have a differential gain error in your detector pair, then that would leak your CMB temperature map. Oh, well, it would leak your sky temperature map into polarization. And if your two detectors are mispointed from one another, that would leak the spatial gradients of that map into polarization. So we use the Planck temperature maps to tell us, what is the true sky signal and temperature. We can calculate what these leakage templates are, fit them from our data at, again, this 9-hour time scale, and subtract it. We also subtract a quadrupole leakage systematic, but that's there. We don't actually regress it out of our data. We use the coefficients measured from BMAP calibrations. So all of this is to say that there's a lot of filtering that we do that goes into our maps to make them kind of manageable, to remove both modes that are very noisy due to atmosphere, but also to remove systematics from things like ground fixed signals or temperature depolarization leakage. So the result, like I said, is that we have maps that are they're not unbiased maps of the sky, and so they have complicated signal transfer function and noise properties that are highly non-isotropic. Again, remember that because we're at the South Pole, we're always scanning in the direction of right ascension. So we have some pretty extreme non-isotropy in our maps. So what we're seeing here is actually a two-dimensional Fourier transform of a Q map. The kind of plus shape structure is just the E modes, the fact that the sky is E mode dominated, and so there's in a Q map there's no polarization for modes with kind of a diagonal wave vector. But on top of that sort of true sky signal of the Q map, we see this missing trench down the middle, and that's exactly the modes that are being filtered out. So these are modes that have a large wavelength along the right ascension direction. These are removed by our azimuth filter. They're removed by our polynomial filter. And so you can just see directly in the Fourier transform of the map the effect of these missing modes. However, an important part of our analysis pipeline is that we also, in the process of this filtering and map making, we build up what we refer to as an observation matrix. Dominic's going to talk about it in a lot more detail. And that's the matrix that encodes all of the linear operations that take us from the true sky to the sky as observed by one of these instruments. And so when we're talking about potential joint analysis of BICEP maps, this is actually a really nice portable description of all the complicated filtering that goes into our map. So if we give you one of our maps, the having that map by itself is very difficult to analyze because you don't you need to know about all this non-isotropic filtering and so on. And this matrix, while it's a large matrix, right? It's roughly n pix squared, though it's somewhat sparse, as Dominic will get into. So it's big, but it's not, nearly as large as, say, a full set of signal Monte Carlo that you could use to also do this. We use it to rapidly generate signal simulations in our analysis. We also use it to solve for pure B eigenmodes in our maps to deal with E to B leakage in our analysis. And then the last note is that you still would also need noise simulations to fully analyze these maps. And in our case, we actually make these what we call pseudo simulations. So we're not simulating our noise just from a random number generator, but we're actually taking our real data and adding it where we've flipped the sign of the data randomly over time using a pattern that would cancel out sky signals, but then would generate, would leave noise. And, you can generate a large number of these random sign flip patterns that are all independent of one another to make multiple realizations of the noise. So the kind of my pitch for, what I think would be the most effective way to share BICEP data would be through the maps with this observing matrix that describes, all the filtering, but then also with some noise simulations that would be needed. I just did jot down kind of, data volumes. If people were actually interested in the time ordered data, is that the raw time ordered data from Keck is something like 93 terabytes. For BICEP 3, it's like 65 terabytes, but still counting. Though that includes lots of things, like calibration data and so on. But even if you tried to reduce it just down to the time streams for the CMB data, Keck is something like 5 terabytes a year, and BICEP 3 is something like 7 terabytes a year in TOD. So it's, the TOD is quite voluminous. And now this observing matrix is maybe 50 or 60 gigabytes or something like that, but that's obviously a huge savings. Okay, I'm going to talk just briefly about what we do in with these maps once we have them, though this is maybe a little bit less relevant to Cosmoglobe in particular, but we actually don't, though Dominic's going to talk about a separate analysis, but in our standard analysis, we don't actually produce a component separated map. Rather, we take these frequency maps, and in fact, we also add in some additional frequencies from WMAP and Planck. And from a stack of frequency maps, we calculate all of the auto and cross spectra, at least for BB, all of the auto and cross spectra. So you'd have n plus 1 over 2 different auto and cross spectra. And then we use that as a reduced data set and fit that to a parameterized model that contains CMB and also foregrounds. Since we're, again, worrying just about polarization, our foreground model is dust and synchrotron. And then we can either do things like solve for a maximum likelihood model, or we can use MCMC and explore, the full posterior parameter space. And, because this is a parameterized model, obviously we have to make it, choice of the model, and we can do things like add extensions, for instance, decorrelation of dust across frequency due to spatially varying spectral index. So this is, it's pretty flexible, but it does, of course, rely on a parameterized model for the foregrounds. So here's kind of a picture of what that looks like in BK15. And so this 3-element triangle plot is just showing the parameters are dust amplitude and a synchrotron amplitude. And so this upper left panel is sort of like, the final result from BICEP, where we have a marginalized posterior for R. And in the BK15 analysis, this led to a 95% upper limit of 0.07. But you can also see, other important features are obviously that we have a very strong detection of a dust signal. Dust amplitude of 0 is ruled out at many sigma. And other interesting things so there's multiple curves on here that show kind of the evolution of this result from our first joint analysis with Planck, and then a couple iterations where the BICEP Keck data, we added in more data. And if you look at this panel that's circled in pink, this is the the two-dimensional R and A dust posterior, and you can kind of see the degeneracy between R and dust sort of melting away as we add new data. And in particular, this was from adding Keck data at first at 95 gigahertz and then at 220 gigahertz, and it helps break this degeneracy. So the one other thing I wanted to bring up, the last bit of my talk, is just to mention that we have been working on joint analyses now with South Pole Telescope. And so in particular, this paper that came out last year was this joint effort to do delensing. So the diagram here from that paper is kind of a schematic of that analysis framework. This was led by Kimi Wu. So the idea was that we actually, so for the delensing, we used the Planck CFV map as a phi estimator to estimate the lensing, the matter field. But then the kind of the sort of new joint part of it was if we have that lensing estimator, we also want to know what are the E modes on the sky that lens into the B mode lensing signal. And there we actually made combined QU maps from BICEP, Keck, SPT pole, and Planck to get the best estimate of E modes, because we want that to be complete over as many modes and as much of and certainly out to higher L than is measured by BICEP alone. Once we estimate what those lensing B modes are, that gives us a lensing template, which is actually then just fits seamlessly into the likelihood framework that I was just describing. So just like we don't make a component separated map, we also don't make a delensed map. We simply include this as an estimate of what the lensing modes are, and that just fits into the likelihood. And so this map level combination that I mentioned is also pretty interesting in the sense of where the information is coming from. So we have, with BICEP Keck, we have this E mode map, which is low angular resolution. You can see the L axis only goes out to 500 here, and is missing these modes that I talked about. With SPT, it goes out to much larger L, obviously still missing modes down at small LX. And then for Planck, that actually can fill in some of those missing modes. And so then when you combine all three of those, you end up with much more complete E mode coverage, which is, of course, useful for then being able to measure as many of the lensing B modes as possible. And then this is just finally the sort of summary figure from that paper that, all of this effort produced only a very small improvement in the R constraint, but that's still so it's in many ways a demonstration of the method, though obviously improvement in the R constraint is great, and very small improvement in sigma R is evaluated from ensemble of sims or in the actual posterior of the real data. Okay, so that's where I'm going to stop, and I should pass things along to Dominic, who's going to talk in much more detail about the observing matrix and the ways that can be used for analysis. I did see there was one comment in the chat, or a couple, but I don't know if it makes sense to take questions right now or to wait until after Dominic's. So Daniel, if you have a
let's wait till after Dominic finishes and we'll come back.
Okay, great.
Yeah.
Okay, so as Colin mentioned, I will use the rest of our time to go into a bit more technical details on this tool or matrix, what you call observation matrix, which, as Colin said, basically incorporates all the operations which is applied on time order data level in the map making. And here is basically written out in somewhat mathematical form. So the idea is basically to incorporate in like a pixel by pixel matrix the effect of filtering and deprojection, basically describing going from a true sky signal or some input simulation QNU maps to these observed BICEP maps. So there are these two operators here in orange, which make this matrix, which make this matrix complex. So first of all, there are these operator pointing matrices forming time order data, and this matrix here forming these pair difference time streams Colin was mentioning. And on these pair different time streams, we act with first this third order polynomial filtering matrix, which is the sparse block diagonal matrix here. Basically, again, to remove the low frequency atmospheric noise in the pair difference time stream. And then there is this ground subtraction template subtraction in this matrix G, which subtracts azimuthally fixed signals and is the sparse Toeplitz matrix. So the product of the two is then neither sparse nor block diagonal complicated matrix. And then the path basically follows the map making by weighting with the inverse variance of the time streams, and then depointing into, projecting it back into a flat sky rectangular BICEP projection, on which then this deprojection matrix acts on. So it subtracts basically templates proportional to the Planck temperature measurement or first or second order derivatives thereof. And then, yeah, in the paradigm of this, of fit and bind maps, transforming this into Q and U maps is then a simple inversion of a rather simple block diagonal matrix. So this full thing is then called the observation matrix, which is then this rectangular matrix by construction, somewhat like 50,000 by 300,000 pixels. As you can see here in the plot here showing the non-zero elements of this matrix, it's quite sparse, so 5% non-zero elements. And yeah, so far in the pipeline, it's used for fast production of simulations or for B-mode purification. But we have started to actually use this matrix to basically correct for the filtering, not later in the power spectrum, like in some master-like framework, but basically using this pixel-pixel description of filtering and deprojection to basically invert the effect and trying to create maps with an unbiased representation of the signal in it. So here's again this view that if you have an input sky here in the E-mode 2D power spectrum, you obtain this low LX filtering here on the right-hand side. So the idea to obtain now a sky signal S, the true sky signal S, is to maximize this likelihood here. So it's a Gaussian likelihood and noise, and adding in here some prior, assuming some external map which is unbiased. So, for example, some Planck map to build this least square estimator, which we solve basically by inverting this large matrix here. So this is now some 300,000 by 300,000 matrix with a preconditioned conjugate gradient. And basically in the most right-hand side, you see the result of that, and kind of seeing the iterative nature of this solver here, and plotting some maximum likelihood estimate of that in a very early stage of the PCG, and then you see how it converges, basically filling in or correcting for the filtering here, especially here in the low LX modes. So here are some simulation results here in the top line showing the filter and bind map as observed. Then basically unbiasing this map, produce this map here in the middle row, and in the bottom row I show the difference with the input showing basically that you get some minimal filtering effects, and just to show kind of the residuals we are getting in form of these stripes. So this is not really the best convergence achieved, but you see how these kind of residuals look like in the stripes in the array direction. And so this basically then shows how the noise looks like after correcting for this filter suppression in the maps, producing these kind of nasty stripes in the noise, basically coming from filling in these are basically coming from the noise fill-in from Planck in this lower LX mode region. And then we have this multi-frequency data set, so we can combine. You can basically obtain a best estimate of a 100 gigahertz, a 150, and a 220 gigahertz map, showing here again how the noise of that would look like. So I've basically ignored for now, or in the previous equations, the beam, but we account for the beam for different beam in the BICEP and Planck maps. To give some numbers, the ballpark numbers are something like 100, 200 iterations. We usually do that, which take about 15 minutes on 24 CPUs. And it's not only really combining it with Planck is not only for filling in these modes, which are badly constrained with BICEP, but it's also about regularizing this matrix inversion and make it much quicker. And basically the goal or the motivation of doing this is to get better comparability with external data sets, and being able to combine on map level. And some kind of work in progress application would be to build a multi-frequency framework where we basically combine all available frequencies we have in some kind of large estimator, accounting for the different scaling of and different assumed sky components, which then results in this estimator where we have to invert somewhat like a 1 million by 1 million matrix, and the memory footprint gets quite large, using basically five of these observing matrices. So I seem I'm out of time, but this is a first simulation result of some kind of an effort to get a CMB component and a dust component map out of like a combination of BICEP, Keck, and Planck maps. Again, you see how you get basically deeper noise here in the center, where basically the BICEP patch is in the map. So in the outer regions, you see the Planck noise as well as these stripes coming from Planck noise. And with that, I can only advertise a talk by SPT, and Marius will talk about more Bayesian view on all this. And